So I'm not allowed to be funny now because it'll be forever and ever down. I'm not funny. All right, means of a plug. This question was answered quite poorly by many. A lot of people, I think, just got a little bit panicky. But whenever they give you a figure, any kind of a figure at all, make sure you pay close attention to it. The mains plug has got 3 safety features. One of these safety features has been ticked on the table already, which meant there were only 2 left. Half a dozen people ticked 3 boxes down here. That meant they were minus the mark. All right. So be very careful when they give you these instructions that you do exactly what they say. If they say draw 1 straight line, they mean draw 1 straight line. If they mean tick 1, if they say tick 1 box, Harry, tick 1 box. If they ask you to put 2 ticks into the figure, put 2 ticks and 2 ticks only. The correct answers were the earth wire, which connects any accidental linkages to whatever metallic casing is connected to the plug, to the earth, to stop us from being shocked, and the fuse, which will melt when there's a high enough current going through your electronics. The live wire is 230 live volts, so that is definitely not a safety feature. It is what allows the joules per coulomb to get into the electronics. And the neutral wire is the return to the power station, so it will always be at 0 volts if you've wired things correctly. This is a charger for a car battery. The meter on the battery shows the current supplied to a battery. That's the key word. As I go through these questions, I look at the keywords that they're giving me. The meter on the battery charger is an ammeter, an ohmmeter, a voltmeter, or a wattmeter. Meter is Latin for measure, so these things are measuring watts, volts, ohms, and amps. The only correct answer is A. The only way you'll know that is if you look at the question. If they give you a figure, sometimes it can contain information, sometimes it's just there to look pretty. This is a look pretty picture. Everybody say, oh. Yeah. I'm going to do 1 or 2 of these maths questions completely, but if needs be, I don't want to run out of time, you see. I want to go to the harder questions near the back. So what I'm going to do is I'm going to do this one quite quickly, and if needs be, we can come back and look at them in more detail. The battery charger supplies a steady current of 2.5 amps. The first thing I do is I'm going to write down every number I've got and the unit beside it to the battery. Calculate the charge flowing to the battery in 8 minutes. 8 minutes. Now, use the equation charge equals current times time. I'm turning that immediately into the symbol equation underneath. Q is equal to I times T. Q standing for the quantity of coulombs in a circuit, I standing for the intensity of the flow, how fast the current is flowing, and T standing for time, the amount of seconds. I'm going to look down at my numbers. 2.5 amps. I know that the symbol for 2.5 for amps, pardon me, is I, and I know that the symbol for time is T. However, we have an issue. Most people lost a mark in this question because they didn't convert those 8 minutes to seconds. I'm going to multiply that by 60. And I'm going to do that in my head for everybody who's listening, definitely not using a calculator because I'm super, super clever. The answer is 480 seconds. It's asking me to calculate charge in coulombs. I'm going to write that down beside it, and I'm going to include my units too. Now I can do my working out. Q is equal to I times T. This is an equation that you'd usually get a mark for, but in your GCSEs, you've got your equation sheet. Q is equal to the number 2.5 multiplied by the number 480. This is my substitution mark. And then I get an evaluation mark, which gives me the answer. Please don't speak. 1,200 coulombs. Now, good morning. Grab your test and have a seat. Yeah, deal with the planner and the whatnot later on. If you write down the correct answer in the white space here, you will get the mark. If you write the answer in this space here, you will get the mark. If you have the correct answer in this white space and then you write the wrong answer in that space, you will not get the mark. Just be aware. Also, can you make sure that your numbers are clear? There was one person whose version of an 8 looks like this. Looks like a 6 when they do it on the page. Just make sure that your numbers are as clear as possible. Otherwise, you're going to be losing out on marks. The transformer in another battery charger has a primary coil and a secondary coil. The voltage across the primary coil is 230 volts. The voltage across the secondary coil is 15 volts. The current in the secondary coil is 3.1 amps. Calculate the current in the primary coil using this equation. I'm going to write down my numbers. 230 volts, 15 volts, 3.1 amps. I'm going to put in my V's and my I's. Because this is about a transformer, I'm going to see which ones are my primary voltages and which ones are my secondary, secondary voltages and currents. 230 volts is a primary, so that's V1. The current in the secondary coil is 3.1, I2. The voltage in the secondary coil is 15, V2. It's asking me to find the primary current. So it's asking me to find I1. Don't know how many amps. Now, this is lovely. They've already done the rearrangement for you. The rearrangement done means that we're not going to get a mark for the rearrangement, and we can just do an immediate swap in. My primary current, we just have a late arrival here, sir. Elliot Brennan just popped in, so he hasn't done his right. Yeah, cheers. Primary current, I1, is equal to the secondary voltage. What is the secondary voltage? The secondary voltage is given to me as 1.5 volts. The secondary current is 3.1 amps. The primary voltage is 230 volts. I've done my straight substitution in. Sorry, I've got somebody trying to get in. Pause. Admit. Close. Continue. Oopsie. Now, I want you to all make sure that you are familiar with the A over B button in these calculators, because the best way to do a question like this is to put it in its fractional form so that you avoid any errors of BIDMAS. If you don't know how to use your A over B button in your calculator, it's just above the 8 when you look at the sharp one that you're going to be using for your GCSE, please come and have a conversation, because that gives us our answer out as 0.20 amps straight away. Edexcel usually have 2 or 3 questions with a lot of writing and a lot of figures. It's important to take your time when looking at the figures and looking at the questions. This is figure 3. It's going to be launching a toy ball. One end of the spring is fixed to the handle. There's my handle. The other end of the spring is fixed to the support. So there are my fixed points. A child pulls the handle, stretching the spring. Figure 4 shows the toy with the spring stretched. So we can see that there is some extension here. Which of these shows the forces acting on the handle when the child keeps the spring stretched? Now, a spring requires 2 forces for it to be compressed or extended, so it can neither be A nor can it be B. Are the forces acting from the handle in towards the handle or out towards the handle? It is D. D was universally answered quite well. Take your time going through these. Look at what's happening in the picture. Harry, can you come and sit up at the front here, buddy? Thank you. Yes. Lovely. Take your time looking at the pictures, looking at the situations. Don't get confused. Multiple choice questions can be very tricky unless you look at them carefully. This is another calculation question. I'm not going to spend time on this. If needs be, I'll come back to it. But remember, it's the exact same thing. Writing down your numbers, checking that the units are in your standard international units, and then doing the calculation. Again, this is another calculation question. I'm not going to spend time doing it, but I will come back and do it if needs be to show people where they went wrong. There's nothing different about this. All my units are all my units are the same, meters, newtons, they're standard international. It's a simple, identify the equation you need to use and then put your number in. These questions were, I'm going to take a bit of a breath if you don't mind, actually. Everyone okay? Enjoying yourselves? Lovely. These 2 questions were almost universally answered quite poorly. All right, now it's no bad. Okay, nothing bad at all if you didn't quite get it this time. It's all about exam technique. Questions in the Edexcel contain context, usually. They contain a command, which is a describe and explain, and they contain a direction. If you keep in mind these 3 things, then you won't get baffled by these questions. And I'll show you what I mean. The child lets go of the handle. The ball starts to move. The spring returns to its original length. Describe the energy transfer that takes place when the ball starts to move. This is context. This is telling you the situation. You've got to visualize it or draw it or think about it deeply, because that's where you're going to find the stimulus to let you get the correct answer. The command word tells you how you have to answer the question. Describe is a command word that says, tell me what's happening, but you don't have to explain why that's happening. Describe what is occurring without having to give me a because statement. And then the direction is what they want you to start talking about. The context could contain lots of physics. They only want you to talk about the energy transfer that takes place when the ball starts to move. So the child lets go of the handle, the ball starts to move, the spring returns to its original length. You've got to talk about energy transfers that are specifically happening in that context. Think about the potential energy stores. So we've got our spring had been pulled back. It's now let go. My ball is moving. What's the first thing that comes into our mind when we've got something moving? Kinetic energy, all right? So something has happened and my ball has got kinetic energy. When you think about any energy transfers, you need to think about the store that was originally there, the transfer that is moving that energy, and the store that it has become. What is the store when I pull a spring back? You've either got, you can call it tension or you can call it elastic potential. We're going to say that the store is potential energy, that the transfer was a force exerted by the spring, and that kinetic energy is the result that my ball got. So it's the energy that my ball had at the end. Context, command, and direction. Whenever you talk about energy transfers, what was the original store? What was the transfer? What was the resultant store? The child can only stretch the spring until the pad is pressing against the support. Explain how the design of the toy prevents the spring from becoming damaged. For this, we're going to look at the design of the toy. This spring can only stretch this far. There is this gap here isn't wide enough for this big pad to get through. How does this mean that the spring won't get damaged? For this, you have to know that there is an elastic limit. There's a limit to the stretch that a spring can have before it has what's called inelastic distortion. There is something called an elastic limit. After that limit, that spring is no longer going to stretch. But hopefully we did that experiment, and if you didn't, we've still got time, where you attached the masses to the spring and the spring stretched and then it sprung everywhere, and it was really fun. And then we got to wear them as crowns if you were in my class, because that's just the way I roll. Everybody say woo. Okay, everybody, thank you. The elastic limit is the point at which the spring will no longer act like a spring. There is a maximum extension that that spring will get to before the elastic limit is reached. After that, the spring will be permanently stretched. You cannot repeat the question. You cannot say damaged in your answer. You have to say permanently stretched because that's the kind of damage. They won't accept answers in your question that refer to the stem of the question. So this part up here is the stem of the question. So the context is about the child only being able to stretch the spring so much, and there's your question. The command was the explain. This is the damage. It's going to be permanently stretched because there is an elastic limit. And this is the direction we got to look at, the design of the toy. Question number 3. How are we doing on time? 20 minutes and not halfway through. All right, we're going to be fine because I can skip some of this maths. Figure 6 shows part of a machine used to separate steel cans from aluminium cans. At this point in time, it's important to look at the figure and to look carefully at what's happening. Here we have a mixture of steel cans and aluminium cans. We have a moving belt that's going around a roller that is also a magnet. Container B contains these gray cans. Container A contains these black cans. The cans are carried along a moving belt. The belt goes around a roller. The roller is a magnet. Each can falls into one of the containers. All of this is context. We have to use this information so that we know what's going on in the image, so we can make a picture of it in our mind, so that we can answer the question. Explain. We're going to have a because statement in this. We're going to have to say why this is happening. We can't just describe what is happening. Explain how this machine separates the steel cans from the aluminium cans. We have to specifically talk about separation. Loads of people were talking about how the machine moves cans from point A to point B, but that's not the context that they wanted. They want to know how the two cans separate. For this, we have to have a knowledge about steel and aluminium. Steel cans are magnetic, aluminium cans are not. We got marks for saying those two statements. Steel is magnetic. Aluminium, not magnetic. We got marks for saying those. This will explain why they will separate. Aluminium is going to go into container B because they're not magnetic. They're not going to keep on going around this corner. If you want the full marks, you can say that steel goes into A and that aluminium goes into B. But the explanation that we had to give here was that there was a different metal in each of those containers and that steel is magnetic and that aluminium is not magnetic. Quite a few people said that there was a scraping motion here, that when these cans hit that point, that they were scraped off. Now that would work, but only if they're magnetic. Okay, the scraping point here will only work if the cans are magnetic. And if you didn't mention magnetism, then you're not going to get the marks. Sometimes these figures can give you hints about what you've got to talk about. Ms. Tovey, right here, this magnetism thing, that was a hint that you had to talk about magnetism. The next step we were talking, this was actually skipped by quite a lot of people because they didn't read the full question. What does RTFQ stand for? Read the full question before you start doing anything, otherwise you're going to feel silly later on. A student investigates magnetism using two toys as shown in figure 7, a toy brick and a toy car. Rubber band, bar magnets, rubber band, north and south. There is a magnet attached to the top of each toy car. The student moves the toy brick towards the toy car. The magnet on the toy brick repels the magnet on the toy car. On figure 7, label the North Pole and the South Pole on the magnet attached to the toy brick. There is your context telling you what's going on. It's important that you spot here in the context that they're going to repel. The command is that you've got to label on the magnet attached to the toy brick the arrangement of poles that will give you the repulsion. North on this side, south on this side. This is the context for part 2 as well. Explain, you've got to give a because statement. Why the toy car starts to move only when the toy brick gets near to the toy car. So we're not explaining why it repulses. We've got to explain why it only happens when it's close. The answer for that, of course, is that there are field lines coming out of my magnets, and only when those field lines interact will there be an attraction or repulsion. What we say there is that there is a field around the magnet that weakens with distance, that depends on distance. So the further away, the weaker the fields, the closer, the better the fields. It could also say that magnets attract and repel when the fields interact. Fields are weaker far away. You could get an idea as well about the lines of force being further apart as well. Here's your context. The student thinks that two magnets on top of each other will produce a magnetic field that is stronger than the magnetic field from a single magnet. The student has a meter ruler and more magnets available. Context, we're going to have to talk about these. Have a seat, get your paper. Describe how the student could develop this investigation to test his theory. Here is your context. This is your command, and this is your direction. We have to make this investigation better to test the theory of, do we think that two magnets on top of each other will produce a magnetic field that is stronger? When you're talking about any kind of practical question, you've always got to imagine that science is an epic rave. Epic stands for the equipment that you're going to be using. Oh, double P, no. What equipment do you need that you're going to be using to measure your dependent variable? What is the things that you're going to be measuring in this experiment? Well, we've got a meter ruler and we've got magnets. We're going to be using the meter ruler to measure. What is the procedure? You have got to tell the people what you are doing. You can't just say a meter ruler to measure. You've got to say a meter ruler that will measure the distance, a stopwatch that will measure the time taken for A to go to B, a thermometer to measure the temperature change over the 10 minutes in the experiment. Whatever experiment you're doing, be specific about what you're doing. The independent variable, what are you going to be changing in the experiment? And think about any control variables as well. How can you make sure this experiment can be repeated more than once where the only thing that has changed, the only two things that are changing are the independent variable that you want to change and the dependent variable that you want to measure. RAVE stands for repeats and find averages. You cannot just say repeats. Dozens of people wrote down the words do repeats, no marks. Repeat and find an average. A repeat is useless without finding a mean. If you don't find a mean, then it, wait for it, means nothing. Was that a real laugh? Jeepers. Right, the student thinks that two magnets on top of each other will produce a magnetic field. Let's think about the equipment that we're going to need for that. So we are going to have a brick with two magnets attached. And it's going to be beside a meter ruler to measure the distance. 2 marks. What are we going to be measuring the distance from? We're going to be measuring the distance from the brick to the car. We've immediately gotten 3 marks here because we've set up the procedure and we've set up the equipment that we're going to be using. Oh, pardon me, we set up the equipment that we're going to be using and we've given specifics about it. Now we've got to talk about the procedure to get our 3rd mark. We're going to move the brick towards car. And we're going to measure when there's a repulsion. Measure the distance, pardon me, where there is repulsion. Repeat with 1 magnet and multiple repeats. That's not spelt right. Find averages. In that, I'm talking a little bit like a computer, but that's all you need to have in physics. We don't care about literary styles, okay? I don't want analogies or metaphors or out like that. That is enough there to get 6, 7, 8 marks. That's everything that you could possibly need. Oh, by the way, also, this mark scheme is going to be available to you. So just jot down the salient points, don't write down everything. These kind of questions come up all the time. Practice them as many times as you can. Remember EPIC RAVE. Equipment, procedure, independent variable, control variables, repeats and finds averages. Here's my big context. The student investigates resistors connected in series in an electrical circuit. The student has a 3-volt battery. It has a 22 ohm resistor, a mystery resistor named X. The student does not know the value of resistor marked X. The student decides to measure the potential difference across resistor X. Figure 8 shows the circuit that the student connected. This is context for all of question 4, so make sure that you're paying attention. The circuit is connected incorrectly. Describe how the student should correct the mistake. If we have got a voltmeter over anything, that voltmeter has always got to be in parallel. Always, always, always. And in this context, we have got a resistor here that we want to find the voltage of. So we've got to say that we need to connect a voltmeter moved to be parallel. And this is the thing that we don't always say, the terminology for this, to be parallel across resistor X. Voltmeter moved to be parallel across resistor X. Whenever we put anything in parallel with anything, we always say that it's measuring the voltage across whichever component is there in the circuit. The student corrects the mistake. The voltage in resistor X is 2.1 volts. The circuit is connected to a 3-volt battery. State the value of the voltage across the 22 ohm resistor. Again, this is just maths. You use the voltage that you're given. Yeah, we'll come back to that in just a minute. The current in resistor X is 0.4 amps. Again, this is maths. We'll come back to that later on if we need it as well. But we're going to hi-ho on to the other questions if necessary. Calculate the power in resistor X. when the voltage across X is 2.1 and the current in resistor X is 0.41. Again, that's just maths, pulling out the numbers, knowing the correct equation. Calculate the overall resistance, the 22 ohm resistor and resistor X. Again, we're going to have a look at that at the end if we have time, so that we can move on to the other questions. Because maths, you can practice and you'll be absolutely fine. Maths, you can practice, you'll be absolutely fine. One thing though, if they say use the equation, use the equation. Down to people who were putting power in there. Seriously. If they ask you to use an equation, use the equation that's given. Don't think they're trying to trick you. Worst comes to worst, if they give you the wrong equation, the exam board have to give you full marks anyway. So win-win. Question 5a. Answered quite well by many. Valiant attempts by a minor few. We'll go to it. Figure 9 shows a small piece of copper about 3 centimeters high. A student wants to determine the density of copper. The student uses a balance to measure the mass of the piece of copper. Here is your context. Here is your direction. Explain how the student could measure the volume of the piece of copper. Now, this isn't an experiment, okay? So epic rave doesn't work. But the first two bits always do. Equipment, procedure. What equipment are you using? What are you going to do with that equipment? You'll always need to think about equipment and procedure when you're doing maths. Explain how we can measure the volume of the piece of copper. People got partial credit for talking about measuring the height, the width, and the length of this piece of copper tubing, multiplying those together to getting volume. This is an irregular object. We can't use the mathematical method for this irregular object. People got partial credit for saying, fill this up with water and then see how much water came outside. It was poured out of it. Again, that's only going to get the volume of the inside, not the volume of the material by itself. The only way to do this is to use your Eureka can or your overflow can. This is a practical that is definitely going to be assessed in your GCSEs if you're doing higher. It might be in foundation too, actually, now that I think about it, but it's good to know it anyway. So, what's the equipment that I'm going to need? We're going to say that we're going to use a Eureka can. Overflow can is as well, or a displacement can too. In my Eureka can, what am I going to do? I'm going to fill to spout with water. Well, with anything. Well, no, yeah, we're going to say water just because. We're going to add copper pipe. Measure overflow. With a measuring cylinder. Equipment, procedure. Measuring cylinder, Eureka can. Procedure. We're going to fill it and we're going to put our copper pipe in. We're going to measure the water that comes out the other side with the measuring cylinder. That's it. 3 marks, happy days. The other alternative as well, you could use a measuring cylinder. You could fill it up with a certain amount of water and see what the volume is. You could pop your copper pipe inside and see that it's gone up to 40 centimeters. Finding the difference in there will tell you that the volume is 20 centimeters, but let's just stick with the Eureka can because it's better. It's more fun. Maths question, answered quite well by the majority. If you're not happy with standard form, get happy with standard form. You are going to have questions that include standard form. You cannot avoid it. It's like death, taxes, and having to talk to relatives you don't like very much. Dennis?
This for period 2, my right to take it.
Go for it, yeah. No worries. So I'm just doing that live thing with this. No, it's all right. Now, one mistake that I saw 3 or 4 times. Listen up. People, and the reason I'm going to do this is I'll come back and do it properly in a second, but they were getting 6.5 times 10 to the minus 6 and then cubing it. The unit meter cubed refers to the unit. It doesn't refer to the number that is being used. So 3 meters cubed is just that. It's not 9. 3 meters cubed is 3 cubic meters of some kind of a volume. It's not 9. It just is 3. So just be aware of that, all right? That cubed is referring to the unit. The other time this can happen is when you're looking at meters per second squared. That's the unit for acceleration, all right? Do not square the numbers that are before that. 2 meters per second squared is 2 meters of velocity increase every second. It is not 4 units of acceleration. Okay, answered by many quite poorly. And the reason I think for that is because we panicked just a little bit. This is the kind of higher tier question that you're going to be getting in your foundation papers. It requires you to do two things. I'm going to do this maths question because I want to show you the amount of effort that it requires to get it. A student wants to determine the specific heat capacity of copper. First thing I'm going to do in my head is, what is specific heat capacity? Specific heat capacity is the amount of energy necessary to increase 1 kilogram of a particular substance by 1 degree Celsius. And if you don't have facts like that off rote, don't panic, you have time. We're going to give you a list of things that you need to memorize based on the definitely possible, on those lists that we sent out. But I need you to know those in your head. Figure 10 shows a piece of copper with a thread tied around it in a glass beaker of boiling water. Thread, boiling water, Bunsen burner, there's my copper pipe. Student leaves the piece of copper in the boiling water so the copper reaches a temperature of 100 degrees Celsius. The student uses the thread to take the piece of copper out of the boiling water. The student puts the hot piece of copper into a different beaker of cold water at 20 degrees Celsius. Here's the apparatus shown. There's my thermometer, glass beaker, water, piece of copper. The student assumes that the thermal energy gained by the water equals the thermal energy lost by the copper. What's that saying? This has got a certain amount of thermal energy, and that thermal energy we've given to it up here in figure 10. The student is assuming that the amount of energy that pops out of that copper is the energy that we just put into it. The cold water gains 1050 joules. Pardon me, the water and copper both reach a temperature of 22 degrees Celsius. The cold water gains 1050 joules of energy. The mass of the piece of copper is 0.058 kilograms, regardless of whether or not you understood a word of that. If you're given a maths question, it's going to be absolutely golden. You want a maths question in an example like this. You just have to know what everything means. Delta Q equals mc delta theta. The change in thermal energy is equal to the mass multiplied by the specific heat capacity multiplied by the change in temperature. You won't be given this in your equations sheet, so it's important that you start learning your units as well. And again, we're going to give, in fact, we've already given it to W2. Everybody who comes into us is going to get a little memory tool to help you memorize all of the equations, or the units of the equations. So let's start collecting my terms. Delta Q is the change, that's not delta Q, that's delta theta, pardon me, is the change in thermal energy. Looking through here, looking at all of our numbers, we've got 100 degrees Celsius, 20 degrees Celsius, 22 degrees Celsius, 150, 0.058. All of these things that we've got. Oh, we all right? Oh, bless you. Delta Q here is the amount of energy that's been transferred, and it's told us here that the water has gained 1050 joules. Delta Q equals 1050 joules. The mass is 0.058 kilograms. The specific capacity is what we're looking for. And delta theta is the change in temperature. This is where people can get confused. We've got two different temperatures, or three different temperatures here. We've got 100 degrees Celsius, we've got cold water at 20 degrees Celsius, and we've got the water and the copper both reaching 22 degrees Celsius. Because we're looking at the specific heat capacity of copper, we're going to look at the temperature change of copper. The temperature change of copper was from 10 down to 22. So the change in temperature, delta meaning change, that triangle means change, delta theta, change in temperature, delta E, change in energy, delta M, change in mass, which probably will never happen in your exams, but there you go. 100 take away 22, 78 degrees Celsius. Now, just looking here, we get a mark for rearrangement and substitution. So this is actually a really awful question if we're not happy with rearrangement. C is equal to delta Q divided by M times delta theta. How do I know that? Because C is happy where it is, M has to move, delta Q has to move, and the way we do this is we're moving them, we're going to move them underneath whatever's on the other side. If you are not happy with this whole process of rearrangement, get in touch as soon as you can. I can teach you how to do this in an hour, and it will mean that you're comfortable with it for the rest of your life. Okay? Open invitation to all who want. I'm just going to move the working out down here then. So we've got the change in energy, 1050, divided by 0.058 times 78, because these are my numbers. We got my mass and my change in temperature, giving me my answer of 200 and I think it's 232 joules per kilogram degrees Celsius. I'm just going to check that. 0.058. 232.095. I often get asked this question. Let's say I've got, this is my answer, 232.0954907. Can you just write down that answer? Yes. Unless they say you've got to give it to a certain amount of significant figures. If they say you've got to give this to 2 significant figures, then your answer's got to be 230. If you're not happy with significant figures, again, come and have a chat. Have we got questions? I'm kind of running out of time. 10 seconds. All right. Right. The value for the specific heat capacity of copper, excuse me. The value for the specific heat capacity of copper obtained from the student's result is lower than the correct value. State 2 ways the experiment could be improved to give a value that is closer to the correct value. Looking at that experiment, what things could we do to make this a little bit more controlled? Any experiment to do with energy, you're always going to get a mark if you mention something about insulation. Some of the heat from that copper will not have gone directly into the water. Some of the heat from the water will have not gone directly into the copper. So we're going to insulate the beaker. To be careful, let's just say we'll insulate with styrofoam and a lid. A lot of people try to say use a more accurate thermometer. Now, while it's a good idea, it's not creditable because we're not worried about the accuracy of our measurements. We're not worried about the accuracy of the temperature measurements. We're worried about the accuracy of the experiment as whole. A couple of things that we could do rather than having water just sitting there, because what happens to water when it's just sitting there? You've got hot water down here, and yes, it'll move up a little bit and the cold water will move down, but then you can get density differences that can mean that just putting a thermometer in one place isn't accurate. So what we might want to do is use some kind of a stirrer. Stir the water while you're having the heating going on. Another thing, while we have hot water inside this glass beaker, what happens when you pick up a glass beaker that's full of hot boiling water? But the glass beaker is hot as well, isn't it? A hot glass beaker. Oh, hello, miss.
I'm sorry to say, can I borrow a Millie for
Can.
a minute, please?
Yeah, absolutely. It's being recorded, Millie, so you'll be able to catch up. Hot glass beaker means that the water isn't just giving energy to my copper pipe. My copper pipe isn't just giving energy, pardon me, to my water. It's also going to be giving energy to my glass beaker. So how are we going to do that? We've got to account for the amount of energy that the glass beaker is picking up. And you don't have to be specific about that. It would require doing an experiment with glass, but you just have to make sure that you account for the hot beaker. My handwriting here is absolutely awful. I'm sorry about this, folks. It's just is what it is. Using a copper pipe to heat, using hot water to heat a copper pipe may not be accurate as well. The hot copper pipe might be 100 degrees Celsius on the outside, but it may not be 100 degrees Celsius on the inside. So maybe put the hot copper pipe into an oven or into a Bunsen burner to make sure that it's thoroughly heated. Anything that we just said there can go in as your second mark. Here's your context. A long piece of wire is made into a coil as shown in figure 12. The coil is connected to a low voltage power supply. Describe how this coil could be used instead of the Bunsen burner in figure 10. Look at figure 10. What's the Bunsen burner doing? A Bunsen burner is heating up the water. People talked about putting the coil directly onto the copper pipe. No marks, because the Bunsen burner wasn't being used to heat the copper pipe. The Bunsen burner was being used to heat the water. So we're going to put the coil in the water, to describe. We don't have to say why or how this is happening, just what we are doing. Describe how this coil could be used instead of the Bunsen burner. Put coil in water. And make a current go through the coil. Because if we put current through a coil of wire, through any wire at all, there's a heating effect. Because when electrons collide with the positive ions, they transfer kinetic and thermal energy to those nuclei in the middle, making that wire heat up.
Do they get to keep the paper, sir?
I don't see why not. I'd probably ask somebody who knows. I don't mind them keeping
I'm
it.
asking you.
We have the scores, don't we? So yeah, let them keep paper. Anyone who's listening, if that's wrong, tell me. All right. We're probably not going to have time to do the maths, but I do have time to have a look at this graphs question and the 6-mark question. Now, I'm going to say this one time, and then what I want you to do is tattoo it into your mind. When you are given a graph, use numbers from the graph in your answer. When you are given a graph, a figure, a bar chart, a line graph, anything, a pie chart, use numbers from the graph in your answer. When you are given a graph, use numbers from the graph in your answer. Figure 13 shows a drone. The drone has 4 spinning blades. The upward force produced enables the drone to rise in the air. The speed at which the blades spin is measured in turns per minute. Figure 14 shows how the upward force produced by the 4 blades depends on the speed at which the blades spin. When we look at a graph, first things first, look at what the axes are telling you. Upward force in newtons on the y-axis, speed in turns per minute on the x-axis. Excuse me. Describe the relationship between upward force and speed shown by this graph. What is the relationship? The easiest way to do this, as x does something, y does something. As x increases, y decreases. As x decreases, y increases. As x decreases, y stays the same. As y stays the same, x decreases. Just have a look at the numbers. These numbers here on the x-axis are increasing. As the numbers in the x-axis are increasing, we can see that the numbers in the y... Oh, that's wrong. Ignore that. That's just wrong. I slipped. As the numbers in the x-axis are increasing, the numbers in the y-axis are increasing as well. As speed increases, force increases. Pardon me. First mark every single time. Second mark, you've got to talk about the trend. Non-linear. Because at 2000, the upward, at 2000 turns per minute, force was, what's that, like 2? But at 6,000 turns per minute, force was 22. Now, Mr. Patrick has put together a lovely lesson about linear, non-linear, proportional, directly proportional. So if we're not confident with that, that's absolutely fine. But when you've got a graph, use numbers. When you've got a graph, as x does something, y does something, linear, non-linear, directly proportional, indirectly proportional, not proportional, and use numbers from the graph. Doesn't matter what the mark scheme says, you'll always get marks. The drone rises from the ground. Pardon me, the drone has a mass of 4.5 kilograms, rises to a height of 20 meters. There are my 2 numbers. Calculate the change in gravitational potential energy when the drone rises to a height of 20 meters. Now, many people got 90 as the answer here. The reason why they got 90 for the answer here is because they didn't see that gravitational field strength was 10 newtons per kilogram. 4 people used 9.81 newtons per kilogram as gravity, which is, while it's correct, meaning you don't get any marks. Because they told you in here that the gravitational field strength is 10. If they tell you, use 10. If they don't, use either 10 or 9.81. The answer to this question was 900 joules. Almost nobody got answers in this part right here. Not very many people got the answer. They love giving you these kind of questions. The amount of energy gained when it raised, so here's my drone, it goes up 20 meters. When it goes up that 20 meters, it gains 900 joules of gravitational potential energy. That is the same as work. So the work done is force times distance. The force is the mass times the gravity. The distance is the height. So that is the same as gravitational potential energy. You just had to write down that it was the same, 900. A lot of times in these physics tests, they require you to use an answer from the first question in the second question and an answer in the second question in the third question. But don't panic. There's something called error carried forward. If you said that the answer to this was 500 and then you used 500 as the energy to be divided by the time in this question, you would still get the marks if you wrote down the wrong answer. 6-mark question. Firstly, I just want to show you how easy it is to get 6 marks in a 6-mark question when you're doing combined science. There we go, right here. Maybe I didn't print the mark scheme for that. Oh no, here we go. You can get 6 marks if you want to by writing less than 20 words, because physics is fun that way. I'm going to show you a 6-mark answer in just a second. We're going to go through the context. The blade and the drone are turned by electric motors. The electric motors are powered by a battery. Figure 15 shows the energy transfers involved when the drone rises from the ground. Battery to motors, motors to blades, blades to whatever the heck that is. Drone on the ground, drone above the ground. Describe the changes in the way energy is stored when the drone rises from the ground. Your answer should refer to energy transfers. Whenever we talk about energy transfers, always it is the store. What is the transfer? What is the new store? And because there's more than one condition here in this little example, we've got a lot to choose from. Now, eyes on the board just for this. 6-mark question could be this. Chemical energy in the battery because that's the kind of energy that we get. Transfers to kinetic energy in motor. Everyone happy with that so far? Everyone happy with that so far? Yeah. Okay. Heat is wasted. To air. 6 marks. 10% of your exam. To get the full 6 marks, you have to talk about energy transfers. Chemical energy from the battery to the motor, or you could have talked about kinetic energy from the motor to the blades, or you could talk about chemical energy eventually going to the blades. Anything along those lines. It's being transferred by, you could talk about individual transfers. So the transfer here is electricity, electrical work from battery to motor, and then forces from motors to blades. If you talked about any of those 3 arrows, any of those 2 transfers at all, you got 6 marks. I never want to see anybody leaving a 6-mark question blank, ever. And this is the way mark schemes are given to us in physics. Eyes on the board. We have what's called indicative content, content that should be included. Chemical energy stored in, and this stuff here is the kind of stuff that we'd expect to see in your answer. It's not an exhaustive list, but it's the kind of stuff we'd expect to see here in your answer. And then we have these levels, level 1, level 2, and level 3. Level 1, basic answer. Level 3 and 4, a basic answer with a little bit more meat in its bones. Level 5 and 6, giving good physics and explaining something. You can get level 1 by saying a single word in some instances. In a higher tier paper, they were able to get level 2, 2 marks, by saying gravity downwards. Right? The only time that it's going to be an issue is if you don't read the context of the question properly. I know that everyone in this room is comfortable saying that a motor moves and a blade moves. Kinetic energy in blades. Kinetic energy in blades would be enough for 4 marks. Or for 3 marks maybe. We can then get this little table. It gives us an idea of possible responses and we can go from there. Rule of thumb for a 6-marker. Always give bullet points. always. Write down at least 6 sentences. Don't have to worry too much about grammar, but you do have to worry about your key words. Spellings don't matter very much in physics. And if you can, use an equation. There's no real equation that we can use here, so we're okay with that. You could maybe hop in efficiency, useful over total, to talk about the the energy being wasted to the air up here in this section. But if you can use an equation, use an equation. All right. I'm glad I skipped the maths stuff, but what I'll do is I'll make a separate video on all those maths questions, and I'll pop that onto Mr. McKelvey at YouTube. Any questions? All right. All together then, everyone say thank you. No, say it really loudly so I can edit it later on so I sound really cool. Everyone say thank you. Thank you. Does somebody want to say I'm the best teacher ever as well? Somebody shout out. Go on. Just go on, Ellie. You know you want to. Did you do